The next issue we'll be talking about in relation to predictor variables is changes of scale. And really, I wouldn't classify this as a problem, but there are times when we decide that we want to change the scale of our predictor variable. So in other words, we take our original predictor variable, we add a number, we divide by something else to get a new variable, xi. So there are some reasons that we actually might want to do this. So one is that it may result in an estimated regression coefficient being on a better scale. So for example, maybe we get an estimate of beta 1 hat of being 3.51 instead of 0.0000351. So this is easier to interpret for people. It also enhances numerical stability. So when you have really, really large numbers or really, really small numbers, the computer doesn't do as well as you would like it to. We like to think of computers as being exact in their calculations, but they can only handle certain levels of precision. And so if your numbers are too big or too small, it's not going to work out so well, and you'll need to scale your data. So what happens when we rescale xi? Well, you might think that this would dramatically change the results of our analysis, but really it doesn't. It just changes the numbers usually by some multiplicative constant. So if we rescaled one of the predictors, it's going to leave the T and F tests unchanged, as well as the estimated variance and the estimated coefficient of determination. All those numbers are going to be the same. However, it will change the estimated value of your regression coefficient. So the original beta hat I is going to be beta hat I times B, where B is the number that you scaled it by in the denominator. If you rescale the response, it's also going to leave the T and F tests unchanged. R squared is going to be unchanged, but both the estimated variance of our errors and beta hat are going to be multiplied by a value of beta. So both the estimated variance and the estimated regression coefficients are going to get scaled by B, the value that we divided our predictor variable by. So let's do a real example so you can see this in practice. So this is the savings example that we started looking at in the previous chapter. And looking back at my notes, I realized we didn't really introduce it a whole lot. So what is the savings data? Well, it's data related to 50 savings-related, actually it's not 50, to 5 savings-related variables in 50 countries, averaged over the period 1960 to 1970. So we're trying to look at savings rates in relation to certain predictors like POP15, POP75, DPI. So POP15 is the percentage of the population under age 15. POP75 is the percentage over the age of 75. DPI is disposable income, and DDPI is the percent growth rate of DPI. So in other words, whether the economy is growing or shrinking, or how much it's growing, I should say. So what we're going to do is we're going to scale the DPI predictor by 1,000, and we're going to see how it affects the different parts of our analysis. So here's our original model. There's no scaling going on so far. And we see estimates of 28.5, negative 0.5, 1.7, negative 1.7, something pretty close to 0, at least on this scale, and 0.409. And so we're going to take the DPI variable, we're going to scale it by 1,000, and I use the I function to do that in my LM statement. And so the I function is a protected function, and essentially what it means is it tells R to do this calculation first, and then add the transformed predictor into the regression model. So I scale DPI by 1,000, and you can compare these numbers to all the previous numbers. They look identical, except that I've taken this number and I've multiplied it by 1,000. So I move that decimal place over 3 places, and I get negative 0.337 instead of negative 0.000337. And as you might expect, this is quite a bit easier to interpret than the other one, though now our scale is disposable income in thousands of dollars, not in $1 units. So what happens if I scale the response by 100? So I'm actually going to multiply SR by 1,000 now. And you can see that now all of our estimated regression coefficients, compared to the original model, not the second model, but for the original model, we're all multiplied by 1,000. But our R squared number is the exact same as it was before, but our residual standard error has also been multiplied by 10, actually, in this case, 100. By 1,000. So actually, it was multiplied by 1,000. And so we have so we've increased the residual standard error by quite a bit of, by a fairly large scale. So scaling the response impacts a lot more than just scaling one of the predictors. And if you want to be very thorough in your scaling or your transformation, goal is to convert both the response variables, both the response variable and the predictor variables to standard units, mean 0 and variance 1, using the scale function. The scale function is a built-in function in R, and that's exactly what it does. It subtracts off the mean from each variable and then divides by the standard deviation so that the variable has mean 0 and variance 1. And if you do that, then your fitted line is going to have to go through an intercept of 0, since your regression line is always going to go through x bar, y bar. But now x bar and y bar are going to be 0, 0, and so our intercept has to be 0 in that case. So what are some advantages of doing this? Well, now all of your predictors are going to be on a comparable scale, making comparisons simpler. So it's essentially, if you want to make comparisons across coefficients, it's like comparing apples to apples. The coefficients themselves can be viewed as a kind of partial correlation. The values are always going to be between -1 and +1. And we also avoid numerical problems that arise when predictors are on very different scales. So we haven't really experienced this problem firsthand in our class, but just yesterday I was struggling with this, where I had x values in the thousands, actually the hundreds of thousands, and I was taking distances between these x values, and I was getting really large numbers. And when I applied the exponential function of the negative distance, I was getting 0. And really, the distance was, the value should not have been 0 because the distance wasn't infinity. But numerically to the computer, the closest it could represent was a 0. And so I was really struggling with numerical accuracy. So sometimes if you scale the response and or predictors, then it reduces the likelihood that you're going to have a numerical problem in fitting your model. But there are some disadvantages. So when you talk about interpreting your regression coefficients, you have to talk about a change of one standard deviation in your predictor. So when you have a 1 standard deviation increase in your predictor variable, then you have some change in your response. And if you standardize the response, you're now talking about the change in the response also in standard deviations, which is not necessarily easy to interpret. So you've got to be careful with that. So what I've done in this example right here is I've scaled all the variables in my savings data frame, and I've stored it into ST savings. The variable names are all the same, but they've all been scaled so that I've subtracted off the mean and divided by the standard deviation. And if we look at a fit of this model, you can see that the intercept is now 0, or at least 4 times 10 to the negative 16th power, which is 0 for all practical purposes. And then we have our coefficients are a little smaller as well. So we can see that the numbers, the numbers are going to change both ways in this case. So we don't get the same numbers as we had before because we have to multiply. Basically, we get interaction between the way that we scaled the predictor variables and the way that we scaled the response variable. And one nice thing that you can do when your predictors are on the same scale is that you can construct a plot that compares your confidence intervals for each of the regression coefficients. And while this doesn't necessarily give you insight into their meaning, it does give you insight into how precisely we're able to estimate each of the regression coefficients since they're on a common scale. If they're not on a common scale, one confidence interval being bigger than another doesn't really mean a whole lot. But when they're on a common scale, then we can compare the confidence interval widths directly. And so in this case, looking at this plot that was constructed using ggplot2, we can see that the DDPI coefficient was estimated most precisely, followed then by DPI, and then these two regression coefficients for POP15 and POP75 were least accurately estimated. So this gives you an idea not only of what the estimated values are, but then how precisely the estimation was done in comparison to one another. When you have binary predictors, you might think about doing the scaling a little bit differently. So, for example, let's say that we've actually already noted that the POP15 variable sort of divides the data into two clusters. So we have the proportion where the countries had less than 35% of the population having an age of 15 or younger, and then we had some that had a population 15 or younger of upwards of 35%. So essentially we had old countries and we had young countries. And so we might create an indicator variable for whether the country is old or young. And in that case, instead of scaling each of the predictors by the mean and then dividing by the standard deviation, we might instead scale by 2 standard deviations rather than 1. And the reason that we might do this is if the probability was half that the binary variable was 0 versus 1, the standard deviation would be a half. And so if we divide by 2 standard deviations rather than 1, then our binary variable, our scaled binary variable, will still be zeros and ones. And so it has a nice, easy interpretation. If we also subtract off the mean, then it's going to get converted to -1 and +1, and we'll have to be careful there. But if we just divide by 2 standard deviations when the standard deviation is a half, then we'll get our binary predictor variable back. So here's an example where I scale some of the variables in my savings model. So I create my age predictor here, which has to do with whether the population is young, in which case the number is 1, or old, in which case the value is 0. So that's all based on whether the percentage of the population that is 15 years or younger is more than 35%. And then I scale the DPI variable by subtracting the mean and dividing by 2 standard deviations, and do the same thing for the DDPI variable. And so fitting this new model with age, DPIS, DDPIS, 2 scaled predictors, then I get a new model. And the way that we can interpret this now, the predicted savings rate is about 5.3% higher for countries with an older population. So actually, that's wrong. It should be the other way around. So when the country is young, POP 15 is more than 35%. So the predicted savings rate is about 5.3% higher for countries with a younger population. So with a younger population. So if we compare our original scaled model, where we subtracted the mean and divided by 1 standard deviation, to the model that we just did, where we divided by 2 standard deviations, then a change of 2 standard deviations in DDPI is equal to a difference of 1 in the new scale of DDPIS. And as you can see, the interpretation is already getting a little bit more complicated. So how would we interpret this? So if we're looking at a typical country, for example, and the growth rate of one was 2 standard deviations more than another one, its savings rate would be about 2.47% higher. So this is now in terms of standard deviations, not just absolute raw numbers. And so in trying to interpret these numbers gets a little tricky. Another way of achieving a similar effect in terms of scaling when you have binary variables is to code them using -1 and +1 instead of 0 and 1. And that way, when you subtract off the mean and divide by the standard deviation, you should get values of 0 and 1. So you once again get the normal binary predictor variable, which is just another way of achieving sort of the same idea. And I'll say personally, I think the second approach makes a little bit more sense, simply because at least then you're only talking in terms of 1 standard deviation instead of 2 standard deviations, which makes a little bit of a difference, and I think makes your results a bit easier to interpret.